So let us see how to construct this operator precedence parser. Remember, for construction of any parser, the input is a grammar. For the given grammar, we construct the parser. Okay. So given a grammar, to construct any predictive parser, there is a restriction. What is the restriction? Grammar has to be free of left recursion and should be left factored. Similarly, given a grammar, to construct any operator precedence parser, remember the grammar has to be operator grammar. What do we mean by operator grammar? Means a grammar wherein there are no null productions on the right hand side or no two adjacent non-terminals. Two requirements: no null productions and no adjacent non-terminals on the right hand side is called operator grammar. Okay. So first we need to ensure that, for example, look at this. A grammar, no production on the right hand side is epsilon or has two adjacent non-terminals. Look at this grammar. Is this grammar is operator grammar? No epsilon rules. First condition is satisfied, but adjacent non-terminals are there. Because of the adjacent non-terminals, this cannot be suitable for operator precedence parser. So, to construct operator precedence parser, the first step is convert this into operator grammar. How do we convert? Ensure that there are no adjacent non-terminals. For that, best part is, since A contains set of terminals, simply substitute for A. Then what you get? E to E plus E, E star E, E minus E and E by E and so on. E exponentiation E, and no doubt in addition to this, add all this E, E, I, D. This is your operator grammar. No null productions, no two adjacent non-terminals. So once you have the operator grammar, what we do is, actually we construct a table called precedence relation table. Precedence relation table. So for that, first try to understand what do we mean by precedence relation. There are three precedence relations defined between any two operators A and B. So when you have three operators less than, greater than, equal to, like this, see, this may look like relational operators, like less than, greater than, equal to. Remember, precedence relation operators and relational operators are different. That's why to distinguish between the two, there is a dot here. The difference is, at any point of time, can you have A greater than B and B greater than A in relational operators? This will never happen, isn't it? When A is greater than B, naturally B can never be greater than A. But whereas with precedence relational operators, you can have A greater than B or B greater than A. Both may happen at the same time. That's why precedence relation operators are different from relational operators. They are not same as relational operators. Now let's try to understand the meaning of the three relational operators. This is A has less precedence to B, A has higher precedence to B, A has equal precedence to B. So what do we mean by A has higher precedence to B? That means A has to be reduced before B. Whereas here B has to be reduced before A because B has higher here. Whichever has higher precedence, that should be reduced first. A, B are equal means both are to be reduced at the same time. Okay. This is the meaning of three relational operators. So given a grammar, by looking at the operators in the grammar, actually we need to prepare a precedence relation table. Okay, we use some procedure like the parsing table construction in LL1. We use a procedure and construct this relational table. Once you have this precedence relation table, the operator precedence parser uses this relation table in parsing the given input stream. Okay, so let us take an example to understand this. So given a grammar, something like E is E plus E, E star E or ID, and input string is something like ID plus ID star ID. Given this grammar and an input string like this, how an operator precedence parser parses this input string by using this grammar means, it takes a grammar and constructs a precedence relational table. A precedence relation table is a two-dimensional array where rows and columns both are operators. Okay, whatever may be the operators you have here, for each of the operator there will be a row as well as there will be a column defined. In addition to that, dollar is also used as an additional row and additional column because we take the string between two end markers. Given a string id plus id star id, we take this between two end markers. Okay, so to parse this input string, what we do is, for this a precedence relation table is formed. We discuss how to prepare the precedence relation table later. Let us take it straight away, the table for this. This is the precedence relation table for that grammar. What are the operators you have? id plus star. In addition to that, we have taken even dollar also because dollar is used as bottom of the stack as well as input right hand marker. Okay. So the entries in the relation table is just precedence relations. You may find some blank entries also. Blank entries always refer to errors. Okay. So given this table, by using this table, let us see how the parser parses. Remember, it is a bottom up parser. The headache here is, at any point of time we should know how the parser can detect the handle. Okay. That is actually given like this. It takes the input string and uses the table, inserts the precedence relation between every pair of terminals. Once it inserts the relation between precedence relation between every pair of terminals, it scans the input string from left to right. At any point of time, whenever it sees a greater precedence symbol from left to right scanning, okay, it stops there and goes in the backward direction till it sees the corresponding less precedence symbol. At any point of time, whatever it finds between a less precedence and greater precedence is the handle. I repeat once again, what it does is, it takes the input string, between every pair of symbols, it will insert the precedence relation by using this precedence relation table. So once you have a string with precedence relations inserted, it scans that string from left to right. While scanning, it goes forward until it sees a greater precedence symbol. On seeing the greater precedence symbol, it stops. Why it stops means, actually that is the right end of the handle. Since now it knows the right end of the handle, in order to know the left end of the handle, now it performs backward traversal. And while performing the backward traversal, how far it continues? Until it sees a less precedence symbol. Why? Because now this is the left end. Hence, whatever it finds between a less precedence and greater precedence is taken as a handle at any point of time. Okay. So let's try to understand the same procedure by using this example. Look at this example. Let us insert the precedence relations by taking this particular table. What is the relation between dollar and id? Dollar on id is less. id on plus is greater. Plus on id is less. id on star is greater. Star on id is less. id on dollar is greater. Now look at this. What is the handle? Now it performs the scanning from left to right. So here, after seeing this greater symbol, it comes back. Whatever it finds between the less precedence and greater precedence is the handle. So here look at this. id is the simplest handle at any point of time. So reduces this. See, so here actually reducing here is something like, within this it is actually replaced by e. Now continues further. So once it goes here you have a greater than greater precedence. So comes back here. Next handle that is detected here is id. So once again reduces that. Similarly continues further. The next handle that is detected here is this. So look at this. What are the terminals you have here? E star E. Look at this. Though there are some non-terminals here, Actually, non-terminals are ignored by the parser because they do not have any role to play. Here the operator precedence parser mainly works by looking at the precedence relations among the operators. Precedence relations are defined only with the terminals but not with the non-terminals. So this string is actually viewed as something like this. So once again the same procedure is repeated. What is the procedure? Between every pair of terminals, take the relation from the relation table and insert. So what is the relation between dollar and plus? Dollar and plus is what? Less. Plus and star? Less. Star and dollar? Greater. So look at this. When you have a string something like E plus E star E, which one has to be reduced first? Star has the highest precedence compared to plus. So first E star E has to be reduced, then E. Look at this. Which way it is ensuring the same thing. So which handle is actually detected first? It scans the string from left to right. Here there is a greater precedence symbol. So scans backward until it sees the first less than precedence. So this is reduced here. So here reducing star is something like reducing E star E to E. Then plus is reduced. This is how the complete string is reduced to start symbol. This is how an operator precedence parser takes the input string and performs these reductions at every step until the input string is reduced to start symbol. So at any point of time, the most powerful tool that is used by the parser to detect the handle is precedence relation table. Okay, so the same thing can be even given as an algorithm. So let us first define operator precedence parser algorithm, then we'll see how to construct the precedence relation table. So the same procedure can be given as a simple algorithm like this. To define the parsing algorithm for any SR parser, you need to define mainly two steps. Why two steps? Any point of time a parser mainly performs two steps, one is shift, one is reduce. So when exactly it performs a shift action, when exactly it performs a reduce action, if you define that, that becomes the parsing algorithm. In addition to that, when it has to halt on successful completion, three steps are required. So when it actually halts, whenever suppose if you consider A as top of the stack and B as look ahead symbol. Okay, so the parser uses a stack, reads the symbol symbol by symbol from left to right. Whenever input pointer is pointing to dollar means complete input string is processed. By the time if the stack is empty, it is successful completion. Okay, so look at this. Shift action when it performs, what did I say? It whenever the relation is less, it has to go read the symbol, compare the look ahead symbol and the input pointer. Whenever the relation is less, just push it onto the stack. Okay, that is shift action. So if A is less than B or A is equal to B also, then push B onto the stack and advance the input pointer to the next symbol. How far this shifting action should be continued? Whenever it is less or even equal to also. Okay, it should be continued until a greater precedence relation is encountered. When a greater precedence relation comes, that is where it has to perform pop. How exactly it performs pop? Popping action here is to take symbol by symbol until a handle is taken out. How does it ensure that a handle now is only two symbols or three symbols or entire stack content? It has to take out the symbol one by one until the symbol that is taken out should be related by less precedence to the symbol recently popped. Whatever you are taking out, once it is greater, take out the symbol until this is satisfied. That is what it means. Repeat, pop of the stack until the top stack is related by less precedence to the symbol most recently pop. Let us try to understand this algorithm by taking the example. Let us take the same example, ID plus ID star ID. So I have the precedence relation table. Once I have the relation table and the input string, by using this algorithm, let us understand how the parser parses this. Given an input string, to identify inputs, end of the input string, append dollar. It uses a stack. In order to identify bottom of the stack, we always use dollar here. Now start reading the symbol one by one. So now dollar is the bottom of the stack, that is A, and the ID is look ahead. Any point of time, compare the precedence between these two. Dollar on ID. What is dollar on ID? Less. Whenever it is less, shift action. So shift the symbol, increment the input pointer. Shift action is just shift the symbol onto the stack and go with the next symbol. Next, ID on plus. What is ID on plus? Greater. Greater means what? Now reduce action. How do we perform reduce action? Take out the symbol. So this is something like this is now reduced by E. Okay. Take out the symbol. Now compare this with dollars. ID on dollar is less. That means only ID alone is the handle here. Just stop and continue. Now you don't have non-terminals are actually ignored. So we should not consider this one. Now what do you have on the start? Top of the stack? It is only dollar. Now dollar on plus. What is dollar on plus? Less. Less precedence. That means whenever it is a less precedence, push it onto the stack and increment the input point. Now plus on ID. What is plus on ID? Once again less precedence. That means push and increment. Now ID on star. What is ID on star? Look at this, greater precedence. That means pop of this and compare this with plus. So plus with ID is less. How far we have to pop up the symbol? Whenever you take out this and this recently popped, these two should be compared. Whenever it is less, see it is a repeat until loop. Whenever condition is true, it comes out of the loop. Since the condition is true, only ID alone is the handle here. Now you have plus and star. Continue with the same algorithm. Plus on star. What is plus on star? Less. Less means push it onto the stack and increment the input point, shift action. Now star on ID. What is star on ID? Once again less. So shift action. Shift action is shift the symbol onto the stack and increment the input point. Now ID on dollar. What is ID on dollar? Greater precedence. So greater means pop action, reduce action. How do we perform reduce action? For reduce action, push the symbol, take out the symbol, okay, pop off the symbol and then compare this with star. Star on ID is what? See, now you have actually ID star plus. If I just reread the stack contents here, we have dollar plus star ID. No doubt ID on star is a greater, that means a reduce action. Now here you may wonder how many symbols actually constitutes the handle. Is it one symbol, two symbols, three symbols? That is resolved by this part. Take out the symbol, pop of the symbol and compare top of the stack with the recently popped one. Star on ID is what? Less. That means that is where you can stop. Next, star on dollar. What is star on dollar? Star on dollar is also greater. That means now the reduce action is take pop of star. Here popping of star is something like reduce E star E to E. Okay, this alone is the handle now. Now you have plus on dollar. What is plus on dollar? Once again greater. That means take out this. Here reduce action is once again reduce E star E to E. Now dollar on dollar is successful completion. So just by using this simple algorithm given any string, by using this relation table, this is how an operator precedence parser can parse the given input string. Now the question is how to construct this precedence relation table. Remember, precedence relation table is constructed based on the actual precedence among the operators. Let us see that procedure. So we use the actual rules of the precedence for creating the precedence relation table. Let's see the rules. Suppose if precedence relation table construction. Suppose if you have two operators, two are of different precedence. Okay, for example like star and plus. Star has higher precedence to plus. Okay, in that case which way we can define is, if theta 1 and theta 2 are of different precedence, like if, then define, suppose theta 1 has higher precedence, we say theta 1 has higher precedence to theta 2 as well as theta 2 has less precedence to theta 1. Example like star and plus. Star has higher precedence to plus, automatically implies that plus has less precedence to star. Okay. And if you have, so this is what you can use when they are of different precedence. The relation between the two operators on either way can be defined like this. If both operators are of equal precedence, if theta 1 and theta 2 are of equal precedence, then what we do is, then we define the rules like this. Theta 1 has greater precedence to theta 2 as well as theta 2 has greater precedence to theta 1 if they are left associative. Whereas theta 1 has less precedence to theta 2, theta 2 has less precedence to theta 1 if they are right associative. So look at this, theta 1 greater than theta 2, theta 2 greater than theta 1, both are possible, which generally is not possible if it is with a relational operators. Why this is so? Take an example. For example, if you take plus and minus are left associative, isn't it? Left associative means what? When you have a string something like id plus id minus id, this should be reduced first, then this. So in order to ensure that the right associativity is considered here, the relation has to be defined like this. So look at this, what is the relation between id and plus here? If these two are plus and minus here, plus and minus both are left associative means what did I say? It should be greater. Okay. So when it is greater, what happens? Whatever you have here, for example, if this is between $2, it will be something like this. So first plus is reduced, then minus. If it is right associative, on the other hand, if you put like less symbol here instead of greater, then what happens? First this will be reduced. Since it is a greater symbol here, left associativity. If it is a less symbol, right associativity. First this one, then this part. Okay. Coming to theta with id and dollar, theta has less precedence to id. That means theta has less precedence to id. That means id has even greater precedence to theta. Next, theta has high precedence to dollar. That means dollar has less precedence compared to theta. And theta left parentheses are right associative. That means theta has less precedence to left parenthesis and left parenthesis has less precedence to theta. And theta and right parenthesis are left associative. That means theta has greater precedence to right parenthesis has greater precedence to theta. And id has higher precedence than dollar. Dollar has less precedence to id. And in addition to this, the relation between this left parenthesis and right parenthesis is right parenthesis is equal to. So in addition to this, the relation between left parenthesis dollar, right parenthesis dollar, id and the left parenthesis, right parenthesis is like this. Between left parenthesis, right parenthesis, always it is equal to. Between two left parenthesis, it is greater. Between two left parenthesis, it is less, because you need to continue. It's only for identifying the particular substring. Remember, between some terminals there will not be any relation. Best example is between ID and ID there is no relation, because we never come across ID followed by ID in any expression. This is for no relations. No precedence relation exists between ID to ID. Similarly, if you take left parenthesis and right parenthesis, that also never happens, isn't it? So, in between these two, for example, when it is ending with some expression, between these two there should be some operator. You will never have only a right parenthesis followed by a left parenthesis. That's why there is no relation between this and this. Similarly, right parenthesis and ID also no relation, because it is an error. Generally in any expression we may have something like ID plus ID, then followed by ID is a wrong one. In between there should be some operator. Similarly, ID and this. So no need of defining any relation between these two, because it is all errors. All blank entries in any parsing table is always errors. So by making use of this actual rules, okay, the precedence relation table is constructed. Let us make use of these rules in constructing the precedence relation table. Let us take an example. So whatever the table we have used earlier, let us prepare that table. ID plus star dollar by using all these rules. Between ID, no relation. ID and plus, what is the relation between ID and operator? ID and operator is greater. And ID and dollar is also greater. Coming to theta and ID, what is the relation between theta and ID? Less. And when you take theta 1 and theta 2, when they are left associative, it should be greater. Next, plus and star. When star has higher precedence than plus, we say plus has lesser precedence to star. Then theta and dollar. Theta has greater precedence to dollar. Coming to theta and ID. Theta and ID is less. And star has higher precedence to plus. Star has, when it is of equal precedence, when both are of left associative, star is also left associative, hence we should use greater. Theta and dollar is what? Theta and dollar is also greater. Coming to dollar on ID is dollar on theta is less, dollar on theta is less, and dollar on dollar is successful completion, hence no relation. So this is how we can get the same table. And though I have listed so many rules, we need not have to by heart all the rules. If you remember the actual precedence among the rules, we can easily construct. Let's see how we can actually prepare the same table here. Take the input string. The way this input string has to be parsed, based on that you need to define the relation. For example, here I need to prepare for ID plus star and dollar. Okay, so given this string, at the first step, what is the handle that is detected here? First, insert this between two end markers. First step, the simplest handle that is to be identified here is IDs. All the IDs are to be reduced at the first level. How do you ensure that all the IDs are reduced? We go in the reverse manner actually. Okay, in order to define these rules, the way we have used the parsing algorithm, whichever the parser has to reduce this input string to start symbol, we go in the reverse manner to define the relations. Okay, because we pretty well know how the expression has to be reduced to start symbol. Okay, that way we can fill the table also. So here in the first step, all the IDs are to be reduced. So if all the IDs are to be reduced first, which way you will ensure? If at all this is to be reduced, put each of ID between less than and greater than precedence. Then only we are sure that this is the handle that is going to be reduced first. So whatever you have kept here, whichever relation you have defined, enter that into the table. Dollar on ID is what? Less. ID on plus is what? Greater. Plus on ID is what? Less. ID on star is greater. Star on ID is less. ID on dollar is greater. These are the relations which ensures that all the IDs are reduced at the first level. Then you are left with dollar plus star dollar. Now in the next step, which operator has to be reduced first? Among plus and star, star has the highest precedence. So star has to be reduced first. Whichever has to be reduced first, remember, any point of time handle is detected by whatever is there between less precedence and greater precedence. So insert the relation like this. Then only this is reduced first, then this. So what is the relation? Dollar on plus is what? Is less. Then plus on star is less. Star on dollar is greater. Okay. And in addition to that, if you take plus and plus, there are few more are missing. No doubt ID on ID is a error. Whereas plus on plus means plus is left associative. Whenever it is left associative, the relation has to be greater. And what about star on plus? Star has the highest precedence compared to this one, and star on star is also left associative, hence this has to be like this. And coming to dollar on star, for example, if I have something like, so if you want to define this one, you can in simple take something like this. If this is the handle, whenever you want to reduce this, this should be under the left parenthesis, less precedence and greater precedence. So dollar on star should be less. Star on dollar should be greater. That's it. So the same table we can construct even by looking at the way the input string has to be reduced. Compare the two tables. Both are same. I think this is missing. So for that also you can take the same thing. Once again, if this is the string, between plus and dollar, it should be greater. What about this dollar on dollar? Remember, dollar on dollar actually, if you remember the parsing algorithm, when A equal to B equal to dollar, it is a successful completion. Okay. So this ID on ID and dollar on dollar are the two blank entries. Generally in any parsing table, all blank entries refers to errors. So here now you may wonder, what is this dollar on dollar? In the parsing algorithm, we said dollar on dollar is a successful completion. And here on the other side, I am confidently saying that any blank error in a table is a error. Two statements are conflicting, isn't it? Though the two statements are conflicting, actually here, no doubt dollar on dollar, if it is occurs at the beginning of the program, that means it is an error. Error here is complete input string is missing. Whereas if this is referred after processing the complete string, that is a successful completion. Okay, so here you should have a flag checking out whether it is referred at the beginning or at the end. At the end means a successful completion, but at the beginning means when you have something like dollar and dollar means there is no input at all. So input is missing, that could be the error. So this is how, once you have a precedence relation table, an operator precedence parser parses this. Now the question is, suppose in my expression grammar, I have so many operators. Then if there are so many operators, the complexity of the table is dependent on the operators. Then if the operators are more, it occupies more space. That's why generally precedence relation table is not stored as a array like this. Instead, it is actually reduced into a simple table called precedence function table. So let us see what is this precedence function table. So the precedence relation table becomes large if the number of operators becomes more, which requires lot of space. That's why instead of storing this n by n table as a precedence relation table, it is actually reduced to a other table called precedence function table. For example, if there are n operators in a grammar, then what will be the size of this precedence relation table? It will be n plus 1 by n plus 1. That one extra is for dollar. So instead of this n plus 1 by n plus 1, what we do is we reduce this into other table called precedence function table. Where now the size is 2 into n plus 1. There are only 2 rows here, columns remains as it is. Okay. So here by each entry is reduced to a numerical value by using two integer mapping functions. Here f is used for mapping the row element, where g is used for mapping the column element. Okay. By using two functions f and g, each value is reduced to a numerical value. Let us check out, like, this is actually the precedence function table for this precedence relation table. Verify whether it is same, both implies the same or not. For example, I want to check out this relation. What is the relation between star and plus? So the same relation, how do I get from this table now? I told you, for reducing the row element, we use the function here, for column g. So to compare this, you need to look into f star and g plus. What is f star? F star and g plus. What is f star? F star is 4 and g plus is what? 1. So 4 is greater than 1, hence greater. That is how the relation is preserved here. Since 4 is greater than 1, compare the two numerical values. That comparison gives you the precedence relation. Let us check out this one. What is the relation here? It is between plus and star. Take f plus and g star. What is f plus? F plus is 2, g star is 3. 2 is less than 3, f plus is 2, g star is 3. So 2 is less than 3, that means the relation is less. This is how actually the same relation is preserved here. But if you compare this table with this table, what is the difference you find? Yes, there is some difference, isn't it? What is the difference? Though there are some blank entries in this table, you don't find any blank entries here. Okay. So while reducing the relation table to function table, even blank entries are also reduced. But are we losing anything with this, reducing this blank entries? No doubt, this is the disadvantage in the reduction. But since these are the blank entries which are referred only on an error, whatever you refer, whether it is right or wrong, it doesn't matter, isn't it? So that's the reason we are not losing anything in reducing the blank entries. But as far as the actual entries are concerned, each and every relation is reserved as it is. For example, I want to check out this one. It is f star and g dollar. F star is what? F star is 3, g dollar is 0. So greater. 3 is greater than 0. You can check out each and everything. Everything is reduced to this particular format only. Okay. Now the question is, when you have a precedence relation table like this, how do we reduce this table to this particular function table? The procedure is very simple. By following a simple procedure, we actually draw a diagram. From the diagram, actually we can, using the diagram, we can reduce this to this. Let us look at that procedure. Since you need to define f and g, two integer mapping functions f and g for every operator, the procedure is like this. The first step is, For every terminal in the given grammar, define two symbols. For example, if A is the terminal symbol, you define FAGA, or if you have plus is a terminal there, F plus G plus, like that. For each terminal in the given grammar, define two symbols, F suffix A, G suffix A, or F suffix plus G suffix plus, like that. So once you create symbols for each terminal in the grammar, the next step is partition that symbols into groups. How do we partition the symbols into groups? By using equal to relation. Let us see how do we use this equal to relation. For example, first step is create symbols for each terminal A as FAGA. Second step, partition symbols to groups using equal to relation. Suppose I have an equal to relation defined between the two operators AB, like this. So how do you get this? From the relation table only. Wherever there is a equal to relation, you have to use that. Then what I do is, remember always row element means left hand side, column elements means right hand side. So here we use F always, here we use G. So when A and B are defined with equal to relation, then we make FA and GB under one group. Next, when there is a relation defined between AC also as equal to relation, then because of this, wherever you have FA, put GC also under the same group. Then what happens? In addition to this and this are there, then we get FA, GB and GC under same group, because FA, GC also should be under the same group. Suppose I have one more relation like C equals to B. Then what I should do? Wherever you have FC, add even GB. Okay. So wherever you have GB, there you have to add even FC also. Because of this, so if all these are satisfied, this many symbols are grouped under same group. Okay, this is how by using equal to relations we combine similar symbols which are defined with equal to as one single group. So once you get the groups, then what you have to do is take every group as a node and create a digraph. So for creating the digraph, you need to have first nodes. Nodes are given by the groups and edges are given by the greater than and less than relations defined in the table. Let us see how do we use that. Take groups as nodes and edges given by less precedence or greater precedence. For example, when A has less precedence to B, then how do you add edge corresponding to this relation? This is function F, this is function G. So from node FA and GB if you take, since the relation is in this manner, that shows even the direction of the edge. What you are drawing is a digraph, so direction of the edge is important. So between these two, this is how, since it is in this direction, that edge has to be added in this way. Otherwise, if I say A greater than B means it should be from FA to GB, since the direction is like this. So for each and every less than or greater than relation, you add the edges. That's how we complete the digraph. So once you complete the digraph, the most important is check for the cycles. If at all there are any cycles exist in the digraph, then immediately stop the procedure and conclude that this particular relation table cannot be reduced to function table. If there are any cycle, you cannot reduce it. If there are no cycles, then only we can reduce this relation table to function table. So how do we reduce? If there are no cycles, length of the longest path from node A gives f of A. From node FA gives the corresponding entity f of A. So this is the simple procedure for converting a relation table to function table. I repeat the procedure. For each terminal, create two symbols FAGA, partition them into groups based on equal to. Then once you get the groups, create a digraph. How do we create? Let the nodes be given by the groups, edges be given by greater than and less than. That greater than less than shows in which direction the edge has to be added. After completing the digraph, check for the cycles. If there are any cycles, you cannot proceed further. You can stop and conclude that it cannot be reduced. The relation table cannot be reduced to function table. If there are no cycles, then take every node, from every node length of the longest path. So here remember, there is nothing like where you need not have to worry where to start and where to end. It is just length of longest path between any two nodes, but should start from a particular node FA. If you start from FA, the length of the longest path gives the corresponding entity f of A in the table. So by using this we can reduce. Let us apply this procedure on this example and let us verify. Okay. So let us take this one and apply the procedure. So what did I say? Create the symbol for every terminal. What are the different symbols you have? FID plus star dollar. So create FID, GID, F plus G plus F star G star and F dollar G star. And after creating the symbols, if there is any equal to relation, based on equal to relation, you need to partition them into groups. In this particular example, there is no equal to relation. That means every symbol is treated as a separate group. So take each of that group as a node. So let us take each of the group. FID, GID, then G star, F star, F plus. See, intentionally I am taking in a different order because there is no serious procedure that you have to take in particular order. What you are drawing is a diagram. The nodes can be in any order. So these are the different nodes. 4 symbols, so 8. 4 terminals, so 8 symbols F and G. Now add the edges. For that, take every row and for every greater than or less than precedence relation, add the edge. So if you take this, how do we add the edge for this relation? FID to G plus. FID to G plus. Next, FID to G star. FID to G dollar. Look at this. 3 relations. So 3 edges are added from F. Coming to second row, this is F plus, this is GID. So GID to F plus. GID to F plus. Then F plus to G plus. F plus to G plus. Then G star to F plus. G star to F plus. Coming to this last one, it is F plus to G dollar. It is F plus to G dollar. Coming to the third row, this is GID to F star. GID to F star. Then what about this? This is F star to G plus. F star to G plus. This is F star to G star. F star to G star. And coming to this, F star to G dollar. F star to G dollar. Third row is over. Coming to the last row, GID to F dollar. GID to F dollar. G plus to F dollar. G plus to F dollar. Then G star to F dollar. G star to F dollar. That's it. If you want to verify, check out the number of relations. That many edges should be there in the graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Number of edges you can check out. There should be 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 edges. So now to reduce this to table, FG ID plus star dollar. How do we get the entries? What did I say? Length of the longest path from a particular node gives you the numerical value. So, for example, if I want to find out f of id, that we say f of id. F of id is nothing but start from the node fid and find out the longest path. See, the path can end up anywhere but should start only from fid. So, if I take from fid, if I take this particular edge, what is the longest path from here? From here to here, it's only 1. Whereas from here, if I take this particular path, longest can be 1, 2, 3. 1 is 3, or I can say 1, 2, like this also. See, 1, 2, 3, 4. The other one is 4, or any other possibility. That's it. And from here, if I take this edge, it is 1, 2. So out of all, the longest is what? 4. Now if I take GID, to get G of ID, start from the node GID. So from GID, look at the possibilities. If I start from here, it is 1, 2 is 1, or I can say 1, 2, 3. If I take this particular edge, it is 1, 2, 3, or I can have something like 1, 2, 3, 4, 5. I repeat, see 1, 2, 3, 4, 5. So I can have 5, or if I take this, it is only 1. So out of all, the longest is 5. Similarly, if I take F plus, from F plus longest is what? 1, 2. And G plus there is only one edge. So 1. F star, from F star 1, 2, 3, 4. F star is 1, 2, 3, 4. And from G star it is, look at this, 1, 2, 3, 1, 2, 3. If I take this, it is only 1, or if I straight away follow, it is 1, 2. If you want, you can write also 1, 2 is 1, or if I take 1, 2, 3, or if I follow this 1. So out of all this, 3 is the longest. Coming to F dollar and G dollar, there is no other outgoing edge, hence 0, 0. Compare the two tables. This is how you can reduce a given relation table into function table. You can compare the two tables, both are same. By following this simple procedure, you can always reduce a relation table to function table, which naturally saves space, just by using two integer mapping functions f and g. So in this relation table, there is no equal to relation. Let us take an example with equal to relation in the table. So let us reduce this relation table to function table. So for that, what we have to do, for every terminal create two symbols FAGA, then use the equal to relation to combine the symbols into groups. Look at this, there is only one equal to relation. So because of that, what happens, which one you have to do? F of left parenthesis and G of right parenthesis. F of left parenthesis and G of right parenthesis should be under the single group. Except this, remaining all symbols should be treated as a separate nodes. Okay, so let us take all the nodes. FA, GA. So here G left parenthesis, then you can have G comma F comma F closing parenthesis, G dollar and F dollar. So because of the equal to relation, Only these two will be under one, remaining all should be in as a separate nodes. If you want to check out of 10 symbols here, 5 rows. So 10 symbols, we get 9 nodes because 2 are combined under 1. Check out this. So here you have 4, this side 5, total 9. Now use that relation table and add the edges. How do we add the edges? Look at this. First row, f of a to g of closing parenthesis, f of a to g closing parenthesis. For this, f a to g comma, f a to g comma, and then f a to g dollar. First row is over. Coming to the second row, g a to f left parenthesis, g a to f left parenthesis, then g left parenthesis to f left parenthesis, g left parenthesis to f left parenthesis. Then no need to consider this equal to. Now coming to this, g comma to f left parenthesis, g comma to f, this is g comma to f left parenthesis, over. Now coming to this, f right parenthesis to g right parenthesis, f right parenthesis to g right parenthesis, f right parenthesis to g comma, f right parenthesis to g comma, coming to this, f right parenthesis to g dollar. Coming to this, look at this, this is f and this is g. So it should be ga to f comma, ga to f comma, and coming to this, g left parenthesis to f comma, g left parenthesis to f comma, coming to this, f comma to g right parenthesis, f comma to g right parenthesis, then f comma to g comma, f comma to g comma. Coming to this, this is ga to f dollar, ga to f dollar, this is g left parenthesis to f dollar, g left parenthesis to f dollar. This is the diagram. Let us now build a relation precedence function table out of this. So fg, the different terminals are a left parenthesis, right parenthesis, comma and dollar. Let us check out f of a. What is f of a? F of a is start from the node fa and find the length of the longest path. So one path is here, it is 1. If I take this particular path, I have 1 as well as 2. Okay, any other? Now if I take this, it is only 1. So longest path here is 2. Now coming to GA, it is 1 here. If I take this particular path, GA to F comma is 1. Then F comma to G comma is 2. G comma to F left parenthesis is 3. So I can say GA to F comma, this is 1, 2 and then 3. Longest is 3. And if you look at the F left parenthesis and G left parenthesis, actually there are no outgoing edges. So we can say this and this as 0. Now if you look at G left parenthesis length of the longest path is 1, 2, 3. Look at this, after constructing the graph, actually we should check for the cycles. There are no cycles in the graph, that's why I am straight away converting that. We have to check for the cycles in the graph. Okay. So for example, if you look at this, this is not a cycle. If it is a cycle, we cannot reduce. Look at this. So G left parenthesis is 1, 2, 3. Next F right parenthesis, F right parenthesis here. Longest path here could be 1 and 2. Next F comma, for F comma longest is 1, 2. G comma, there is only 1. And F dollar, G dollar, no outgoing edges, so 0, 0. This is the precedence function table. So even if there is a equal to symbol, equal to relation, combine that symbols together into one node and then continue with the same procedure. So this is how we can construct an operator precedence parser. Remember, operator precedence parser is very simple. It is of restricted use. It is preferred only for the expression grammars. So if the expression grammars are there, this is most efficient. And this is one of the bottom up parsers which can be used only for the parsing the expressions. But the restriction here is to design operator precedence parser. Remember, grammar should be an operator grammar. So before we close this topic, let us look at one interesting question which was asked in previous GATE question.